Oh my goodness, you're probably wondering, are you even in the same class anymore? What is he thinking about giving me this type of problem to go through and solve? This is craziness. It's actually not. It just takes a little bit of practice. It takes some time getting used to, folks. I know that. So just bear with this process a little bit. It's going to take some time to get the rust off, so that way your organic gears can go fluidly into the future. Okay, so we left with this problem. I'm going to take this alkyne with this random alkyl group, and I'm going to add this random alkyl group that's attached to a bromo, and then I'm going to end up with that mess over to the right-hand side? 2,6-dimethylheptane? Yes, that's what we're going to do, and this is how we're going to do it. So, first off, I told you, write down the map. Write down your plan. Number one, we're going to have to elongate the chain. We've got to. We clearly can see that, folks. We elongate the chain. Not only that, it tells me you're going to have to elongate the chain. Well, again, they're giving me the R group that's here that I can pick from. Well, why can't I just pick all 7 carbons? Okay, well, you could. If that's what you want to do, pick 7 carbons and put them there. So 1, 2, and then add 5 more. And then you're thinking, well, I don't have to elongate the chain if that's the case. Yeah, you do. Because look, they're telling you you're going to have to add on another carbon piece. That's a requirement of this reaction. It's telling me that. So I cannot start off with 7 carbons. It's not going to let me do that. Because in this step, that requires another carbon. So if you start off with 7, you now have ended up with 8. At least. So we're going to have to elongate at some point in time. This is how we're going to elongate, though. I want you to look at this product. Have we ever talked about a way that we can just slap on a CH3? No, we haven't. We've talked about adding on H's. We've talked about adding on OCH3s with alcohols. We've talked about how to add on OHs with things like water. We've talked about how to add on bromo groups and chloro groups. But never, at any point in time, have we talked about how do we add on groups that are like CH3s only or CH2CH3s. We haven't really done that. Only in the process of elongation have we been fiddling with carbons. That's it. So this is a very good sign of what I need to bring into the picture with my R groups that are stated on my reactant side of the house. If they're going to let me pick any random group that I want to pick, you better believe that one of the things that I'm going to ensure of is this piece. At least, if I can bring in this group over here on my R piece, and they allow me to do that, then that R will bring with it this CH3, that isopropyl group right there. And I don't have to worry about getting that CH3 onto that molecule. Okay, well, if that's the case, I've got another one over here, right? How on earth do I get this one? That's not going to be a problem with the same reasoning. This isoprop group here, CH3, look, I have another chance to pick an R group. And if I can pick that kind of formation right there, then I'm pretty good. That will bring into the picture that whole L-shaped group that I need to worry about in my product. So I need those to be involved in the R groups as much as possible. Now, we've got, if I do this, 2 carbons that are involved in this triple bond. Well, I've got this carbon, and this carbon that's left. So what does that mean? Well, that's up to you. 2 of those 3 carbons had to be a triple bond at some point in time. They had to be a triple bond at some point. Do you pick the first 2? Do you pick the second and third one? That's up to you, folks. I don't really care. Honestly, it doesn't really matter. You could go either way with it and you would be correct. So what I'm going to do is I'm just going to target the first two. I'm going to target this one and I'm going to target this one, and we'll see what happens. All right, maybe that's right, maybe it's wrong. We'll see that when that time comes. But the two carbons involved in the triple bond, these are the two that I am going to worry with those. So what that means is that this, if those two carbons are my triple bonds, my carbon, triple bond, carbon, hydrogen, right? What kind of R group do I bring along with that? I bring on the CH, CH3, CH3. All right, so here is my first piece that maybe I want to play around with in the synthesis. It tells me I can pick anything I want to pick. Well, I know that if I pick this piece, I don't have to worry about adding methyl groups because I don't know how to do that yet. So that comes along with the whole alkyne. Now, let's take a look at this side, this R prime Br. If these are the two carbons that are part of the chain elongation step, then that means that I have this extra carbon to worry about right there. We already said the R group could take care of this isopropyl configuration, but I'm missing a carbon if that's all that I add. So that's okay. We'll just add on another carbon, and that is the R group that I will pick to go along with my bromine. Okay, not a big issue at all. CH3, CH, CH3, my CH2 with the Br on it. There's my two pieces. However, this is not it of the reaction. So what I'm saying is don't let this confuse you. Some people will look at this and say, I only have to do one step. There's no way I can go from that to that in one step. No, they didn't say one step. This was part of a multi-step synthesis problem. That question mark means you bring in whatever you need to bring in to get this done. It's kind of like having that mean boss and you're assigned a job and you go to them and you say, I don't know how to do this. And they look at you and say, get it done. That's what this question's doing. Get it done. Get her done. So if I can take these two pieces and I can react them together, then this will help my chain elongation, but I am nowhere near the product yet, which means that there's some extra steps that I'm going to have to take throughout this process. All right, so if I take these two pieces, how on earth do I get these two things to react together, right? Well, I need this to be an ion. And the only way for that to be an ion is, number one, use sodium amide, NH2. That's what we have to do first. All right, so I'm going to go to this screen. Let's clear it out to give us a bigger working room. And I'm going to take CH3, CH, CH3 with a carbon triple bond carbon hydrogen. There's the alkyne that I want to start with. And I'm going to add NH2 to that molecule. The purpose of the NH2 is to take my alkyne, which is going to behave like an acid, and it's going to donate its proton. And this is what I end up with. It is the acetylide ion again, but this time on the left-hand side, it's bringing some more carbons with it, which is perfectly fine. That's okay to do. Not a big issue at all. All right, so that's step one. Step two, I'm then going to take that piece and I'm going to have to figure out what kind of bromide do I add to it to get my product. We've already figured this out. All right, we said we need the CH3, this carbon with another CH3, and then a CH2 with a Br on it. We said we had to pick that in order to get the correct total number of carbons in the end. So when these two pieces come together, this negative carbon is going to attach at this carbon that has the bromine on it. That's where my pieces get glued together. That's the chain elongation step. So I've got a CH3, a CH, a CH3 that points down, or up, doesn't matter, same thing. A carbon, triple bond carbon, and that carbon is attached to that CH2. That's attached to that CH. That's attached to two methyl groups. One over to the side and one that we've drawn down again. Folks, we're getting closer, right? Look at this. We're getting closer. The problem at this point is that this molecule has a triple bond. And our product did not have a triple bond. It was single bonds all the way across. I mean, that's what it was. Let's go back and take a look at it if you don't believe me. Look. All single bonds all the way across. There are no double bonds. There are no triple bonds. Nothing is there. So now the question is, how do we go from this to single bonds all the way across with nothing else added to it? No bromines added, no chlorines added, no OHs added. Nothing. Just completely destroy the alkyne to an alkane. Well, I hope out of your Batman tool belt that you say, well, Tracy, you know, we could take this triple bonded molecule and we could destroy that triple bond in one fell swoop. And the way that we do this, you just taught us this because you're a great instructor and you just gave me all the details that I needed to know, is I'm going to take H2 and I'm going to take platinum. Ping, ping, ping. And that triple bond breaks down to a single. All the way through. It doesn't even stop. The only way it stops is if I add H2 Lindlar. So I'm going to redraw my reagent. There we are. And the first round of H2 gets added on. So my double bond breaks, or triple bond breaks to a double. Two sites of attachment open up. Here, here. H goes on one side, H goes on the other. Like I've said before, folks, we don't have to worry about writing H's. We understand that they're there, so I can erase them. And then another round of H2 platinum is going to get added. So my double bond goes to a single bond, and two more sites of attachment open up, here and here, and H goes there, and H goes here. And I don't have to write those H's. They are understood to be there, so I'll just get rid of them. But this is a condensed structure. They are writing hydrogens. We'll just kind of condense them down, and I know that at this point that carbon has to have 2 and this carbon has to have 2. And there is the product that I need from that question. Now, let's talk big. Big pants. Let's put our big pants on. You ever see the Saturday Night Live? I got my tight pants on. Well, we're going to put our big pants on. So up here at the top, let's talk like real organic synthesis. Synthesizers. What I have here is a 3-methyl 1-butene reacts with sodium amide in an acid-base reaction where the sodium amide deprotonates the 3-methyl 1-butene. And we end up with the 3-methyl 1-butene ion, or the acetylide ion for short. The acetylide ion will then react with this molecule, which is a 1-bromo 2-methyl propane, in a nucleophile electrophile reaction, where the acetylide ion is the nucleophile and the carbon involved in the polar carbon to bromide bond serves as the electrophile. When these two things react, I end up with this molecule, which is a 1, 2, 3, 4, 5, 6, 7 heptine. Then on carbon number 3 is where my triple bond is at. And then on carbon number 2, 3, 4, 5, 6, I have 2 methyl groups. So it forms a 2,6-dimethyl-3-heptine. The 2,6-dimethyl-3-heptine then reacts in a hydrogenation reaction with hydrogen and platinum to give me the product, which is a 1, 2, 3, 4, 5, 6, 2,6 dimethyl heptane. Was that okay with you? 3-methyl-1-butane reacts with sodium amide. The sodium amide deprotonates the 3-methyl-1-butane in an acid-base reaction to give us the acetylide ion. The acetylide ion will then react with 1-bromo-2-methylpropane in a chain elongation reaction where the acetylide ion serves as the nucleophile and the 1-bromo-2-methylpropane serves as the electrophile. Those two react together to give me a product of 2,6-dimethyl-3-heptine. That alkyne will then undergo a hydrogenation reaction, and when it does, it will form a 2,6-dimethylheptane because the alkyne has been completely destroyed to an alkane. Whoa. Could you follow that? Was that kind of easy for you? Did you understand that language at least? If so, good for you. You are turning into organics. Again, I am worming my way into your brain, slowly but surely, and I'm sneaky about it like that. Look at all the stuff that you've learned. Nucleophiles, electrophiles, acid-base, nomenclature of alkanes, nomenclature of alkenes, nomenclature of alkynes. We can go through and talk geometry and talk about sp, sp2s, and sp3 carbons. If that's what we wanted to do, we could do that. But more than that, we have just done another synthesis problem. We have taken something simple, like over to the left, and made something that looks pretty complicated over to the right. Okay, let's look at another. What about this? Here's another problem. It might take more than one step. If so, that's fine. We just got to figure out what it is. And to the left-hand side, I have this ring structure, which is okay. I've got an alkyne on it. It tells me what alkyne that I have to use. I have to use it. And then it gives me a question mark. And it says, what do you need? You tell us. We're not going to tell you more than one step. We're not going to tell you anything. You tell us what you want to do. Okay, well, this looks pretty simple, right? I mean, it looks like I have a ring structure here with 2 carbons on it. And then my product side is a ring structure, the same ring with 2 carbons on it. So do I have to do chain elongation? Probably not. I have the exact number of carbons that I need. We don't need chain elongation here. Whew, that saves me that step. So then you're going to look at this and you're going to go, oh, okay, so we need to add the OH group on. I know how to add OH group on. Okay, so I'm going to take this ring structure and I'm going to take that alkyne, and I know that I can add OH by adding something like water. Not a big deal, water and acid. Okay, so I'm going to start off with my ring, and I have that carbon, triple bond to that carbon. And I know, because you told me, Tracy, that a couple of videos back, this triple bond is going to break to a double. And here, the H plays with other H's. So it looks like my hydrogen will go here and my OH will go there. That's not where you want the OH to go, is it? So that's not going to work. My OH is in the wrong position here. Scratch it. That ain't going to work for us because it puts my OH group on the other position. So I know that water and acid will not add on the OH group the proper way. Then you're going to say maybe, hey, well, what about this mercury sulfate? I know that mercury will add on OH. It does. And that mercury sulfate will break the triple bond. A double will form. Two sides of attachment open up. H plays with other H's, and OH goes to the other job. It's a Markovnikov reaction. It gave me the same thing that water and acid did. Isn't that what I told you anyway? So you should have known that one. All right, so that's not going to work. Well, how do we get OH group to go on the other side? Well, you might say, hey, we'll do anti-Markovnikov. And anti-Markovnikov is things like BH3 and THF and OH and H2O and H2O2. Yeah, that's right. You can do that. So if I did that setup, my triple bond would break to a double. Boink! There it goes. Two sides of attachment will open up here and here. And H does not play with other H's. Remember, it goes, ew, I don't like you. It's anti-Markovnikov. So hydrogen will be forced to go here, and OH would be forced to go there. And then you're like, I've got it. No, you don't. No, you do not. If I had a ruler, I'd be slapping right now. Slapping your hands. This is not the product that you're after. Why? Folks, it's got a double bond. It's right there. I don't have a double bond up here. Then you might say, well, that's easy to fix. I just take this and I would add H2 platinum to it, and that will destroy the double bond. Wrong, 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 wrong. Why is that wrong? Because, folks, look at what you've made here. You have made a molecule that is an enol. C double bond C with an OH. What do enols do? If you go this route, that double bond would shift, that C double bond O would form, just like we've done many examples of over and over, and this is what you would end up with, a C double bond O. We do not have a carbonyl in that product. This is not going to work. It would have worked. It would have worked if that double bond was not there. If that double bond was not at that position, we would not have formed an enol. And that would have prevented that from happening. Okay, well, that's an easy fix. If this was a single bond, OH would have stayed, and that's what we needed. Which would mean this needed to be a double bond right here, which would have meant we needed to destroy that double bond first. So we're missing a step. What is that step? I need to take my ring structure. I need to take the alkyne that they told me to start with. And the very first thing that I need to do is Lindlar it. I need to Lindlar that triple bond in order to get a double bond first. That is how we do this. Now, I didn't have to do H2 Lindlar. I could have done the ammonia version with the sodium at really cold temperature. It didn't say cis or trans. It really didn't care. Either one of those routes would have worked. That's just another possibility. But I need to take the alkyne and I need to go to the alkene first. All right, so this gives me a CH2 here, and it gives me a CH there. Hydrogen goes on one side, hydrogen goes on the other. So now, that's what I'm going to start with. I've got this CH group that is a double bond. I now can react BH3THF to that. That double bond will break to a single bond. Two sites of attachment will open up like we planned. H does not play with other H's, so it definitely goes left just like we planned. And OH group goes on the end just like we planned. No difference. And that's what we'll end up with. Now, if you did not catch the H2 Lindlar, there would be no other way to get this OH group on there. That would have forced you to have a double bond, And OHs and double bonds are enols, and they will rearrange every single time on you. That's just the way it is. I also want you to know that this was a CH. I didn't correct it, but I'm just assuming that you know it's there. This started off to be a CH. We've added another H, so that is a CH2 that's right there. And then over here to the right-hand side, it started off as a CH2, so it's still a CH2 over here. I just went back and I didn't clean up that product, but don't get confused. That is what they want, and that is the product that they're after. So in this reaction, I'm going to start off with that alkyne. With the alkyne, I'm going to H2 Linlar it to create an alkene. Once I get the alkene, I'm then going to undergo hydroboration oxidation, and that will form the alcohol product that we are after. Okay? All right, so there's you another example of multi-step synthesis. Now let's take a look at this. I really like these. If you can tell, they might be getting a little trickier and trickier. They're like little brain puzzles. Think of these as little games. That's how you need to do it. That's how I learned math. That's how I learned organic. I just thought of them as a little brain teaser puzzle. Kind of like those ones that you sit down at Golden Corral and do. Which I cannot stand. I lose every single time that I try to play one of those. So in this example, we are starting with an alkyne, and it tells me what I have to start with. It just point blank tells me. Carbon, triple bond, carbon. That's all you get. You just get acetylene. That's all. What do you do to give me that product to the left or to the right? Oh, gosh. Look at what they've done. They a lot of steps maybe or possibly going to go into this. That's okay. We know how to do all of them. It might just take a little bit of more digging, and we need that shovel ready. But we can do it. So as last time, I'm stopping the video here. Write down this example. Can you come up with a way to make that product? Look at the things that you have to do. You know you're going to have to elongate a chain, right? You're going to have to do that somehow. We also have to bring into play a little bit of cis or trans, because they're giving me those shaded and dashed wedges. And it looks like the hydrogens are on the same side because they are both on dashed wedges. So how do we make sure that the hydrogens go onto the same side of molecule? There's a route for that. We know how to do that now. And then in addition to that, we've also formed this the CCO relationship. This love triangle. We called that a peroxide, or epoxide, sorry, an epoxide. How do we get epoxides onto a molecule? We know how to do that too in the world of alkenes. It's one of those reactions we discussed. All of it's fair game, folks. Every bit of it. So I'm going to leave you with that. Those are my hints. So see if you can come up with a plan. How do you go from the one on the left to the one on the right? Think of it as a game, puzzle pieces that you have to fit together, and see what you can come up with. Good luck.